Hi, in this video we are going to study the Shannon Interpolation Formula, which is an expression for the representation of band-limited signals in terms of the samples of the signal. Now, in order to obtain this result, we remember the details of the Shannon sampling theorem. Well, as we remember, our starting point is a band-limited signal, x of t. So x of t is a band-limited signal, which means that its Fourier transform is non-zero in a band of frequencies and zero outside this band. So x of omega is 0 for absolute value omega greater than omega m, or omega greater than omega m and omega less than minus omega m. Such signals are called band-limited signals because they vanish outside the band of frequencies. The Fourier transform vanishes outside a band of frequencies. Now, from x of t, we obtain the sampled signal, xs of t, which is m from minus infinity to plus infinity, x of m ts delta of t minus m ts. So we have the sample signal, but what kind of a sampling do we have in this case? We have sampling by an impulse train, periodic impulse train. The periodic impulse train is p of t, which is the expression m from minus infinity to plus infinity delta of t minus m ts, and therefore xs of t is the product of p of t and x of t. Now remember the statement of Shannon sampling theorem. If omega s, which is 2 pi divided by ts, is greater than 2 omega m. Remember, ts is called the sampling period and omega s is called the sampling frequency. So if the sampling frequency is greater than 2 omega m, x of t can be reconstructed from xs of t by means of an ideal low-pass filter with the following frequency response: h of, or let us call h sub LPF, meaning we have the low-pass filter action. This is equal to Ts for absolute value omega less than omega s over 2 and 0 otherwise. So if xs of t is applied as the input signal to this ideal low-pass filter, the output is x of t. So x of t is recovered from its samples. This is only possible if omega s, the sampling frequency, is greater than 2 times omega m. Omega m is, remember, the highest frequency component in the spectrum of x of t, the Fourier transform of x of t. So when xs of omega is multiplied by h LPF of omega, the result turns out to be x of omega, or x of omega is reconstructed from xs of t. Now, we have seen this in the video related to the Shannon sampling theorem with all the details. Now, in this video, we are going to see the time domain version of this last expression. Okay, so let us consider the time domain version of this expression. Remember, in frequency domain, if we have multiplication, in time domain, we have convolution. Okay, so xs of t convolved with h LPF of t is equal to x of t. Okay, where h LPF of t is the impulse response of the ideal low-pass filter. Okay, so how can we calculate the impulse response? We can use the inverse Fourier transform. So h LPF of t is the inverse Fourier transform of capital H LPF of omega, or it is from minus infinity. Okay, we have also the factor in the inverse Fourier transform, the constant 1 over 2 pi, from minus infinity to plus infinity, capital H LPF of omega e to j omega t integrated with respect to omega. So this turns out to be 1 over 2 pi from minus omega s over 2 to omega s over 2 ts it's equal to the constant Ts in that interval, e to j omega t integrated with respect to omega. So this is Ts can be taken outside the integral, Ts over 2 pi, and the integral of e to j omega t with respect to omega is e to j omega t divided by jt, evaluated at minus omega s over 2 and omega s over 2. So this is equal to Ts over 2 pi is 1 over omega s, and we have e to j omega s over 2 t minus e to minus j omega s over 2 t divided by j t. So this can be written as 1 over omega s. Now the numerator can be written as 2j sine omega s over 2 omega s t over 2 divided by jt. So j's will cancel out. So h lp f of t, the impulse response of the ideal low-pass filter, turns out to be sine omega s t over 2 divided by again omega s t over 2. Okay, so the impulse response of the ideal low-pass filter is in fact a sinc function given in this form, sine omega s t over 2 divided by omega s t over 2. Okay, now in order to verify the Shannon sampling theorem, now we know that the convolution of xs of t with this impulse response of the ideal low-pass filter will give us x of t. So let us look at the details of this computation, which is known as the Shannon Interpolation Formula. Okay, we have seen that the band-limited signal x of omega can be obtained as the output signal of the ideal low-pass filter with frequency response given by capital H sub LPF of omega multiplied by xs of omega. So xs of t is applied as the input signal to the ideal low-pass filter, and the output is x of t. So this is the frequency domain expression. So in time domain, we obtain x of t as the convolution of h LPF of t and xs of t, where small h sub LPF of t is the impulse response of the ideal low-pass filter. And we have calculated the impulse response of the ideal low-pass filter as sine omega s t over 2 divided by omega s t over 2. Now, remember that omega s is equal to 2 pi over ts. Capital Ts is the sampling period. So if we substitute this in the impulse response expression, h LPF of t becomes sine pi t divided by ts divided by pi t divided by ts. Okay? And now we are able to express this function in terms of the sinc function. So this is sinc of t divided by ts. Okay, now xs of t was equal to m from minus infinity to plus infinity x of m ts delta t minus m ts. Now we know that for the ideal low-pass filter, if the input is an impulse, we get the output h sub LPF of t. And by using the time invariance of the system, the ideal low-pass filter is linear and time invariant. That of t minus mts will give us the output h LPF of t minus mts. Okay, therefore x of t, which is the convolution of xs of t with the impulse response h LPF of t, will be in the following form: m from minus infinity to plus infinity, by using linearity and time invariance of the system, the ideal low-pass filter system, x of m ts h LPF of t minus mts. Okay, so if we substitute the expression of the impulse response, x of t turns out to be m from minus infinity to plus infinity x of m ts sinc t minus m ts divided by Ts. Now this expression, okay, let us put it in a box. This expression is known as the Shannon Interpolation Formula in the literature, because as we see from this expression, we express the signal x of t, which is the band-limited signal, in terms of its samples weighted by shifted sinc functions. These sinc functions are in fact coming from the system action, the ideal low-pass filter system action. So each shifted sinc function is multiplied by the sampled value of the signal, and we have a superposition of all these terms. So it is an interpolation formula. And this formula is known as the Shannon Interpolation Formula. Also in the literature, it is sometimes referred to as the Whittaker-Shannon interpolation formula, because a British mathematician, Whittaker, obtained similar results before Shannon. But when we look at the expression, we clearly see that the signal, band-limited signal x of t, is in fact represented in terms of its samples. In other words, we reconstruct the signal by using its samples and by using this interpolation formula. So in a way, this expression summarizes all the theory we have developed so far, namely, first using a signal model xs of t that we obtain by sampling x of t by an impulse train, and then using the ideal low-pass filter to recover x of t from xs of t. In fact, this is only a model. That means we cannot obtain an impulse train in reality, which is not a physically realizable signal. So we are working with signal models in developing sampling theory. But as long as the condition omega s greater than 2 omega m is satisfied, that means omega m is the highest frequency in the spectrum of x of t. If the sampling frequency omega s is greater than 2 omega m, we are able to reconstruct the signal without any information loss from its samples. And this single formula just tells us this fact. Okay, thanks for watching.